Welcome. Thanks for joining us here at the Z-Files. Before we begin, let's settle in with a curious thought. Some engineering works of ancient peoples are so enormous and so precise that even with all our modern knowledge, we're still piecing together how that was achieved. These monuments are patient riddles, waiting in the desert sun and mountain air, holding secrets not of magic, but of ingenuity, sweat, and unknown techniques. Let's explore these mysteries quietly together. Part 1. The Stones of Baalbek. In the mountains of Lebanon, in a place called Baalbek, 3 stones rest in a temple wall. Each weighs over 800 tons. They were placed there more than 2,000 years ago, fitted so tightly that a blade cannot slip between them. The Romans built a grand temple complex on this site, layering their columns and courtyards atop foundations that may be even older. But these 3 blocks, known as the trilithon, remain the most puzzling feature of the entire structure. They are among the largest worked stones ever moved by human hands. The stones came from a quarry less than a mile away. We know this because one block, called the Stone of the South, still lies there, partially carved from the bedrock. It weighs an estimated 1,000 tons. The quarry shows clear tool marks, chisel grooves running in parallel lines across the limestone surface. Ancient workers carved channels around the block, isolating it on 5 sides, leaving only the base attached. Then they stopped. Why they abandoned this stone is unknown, but its presence teaches us something important. The ancients did not rely on mystery. They relied on patient, methodical stonework. Moving an 800-ton block presents extraordinary challenges. Modern cranes can lift such weights, but they require steel, hydraulics, and engineered supports. The Romans and their predecessors had none of these. They had wood, rope, bronze tools, human muscle, and possibly animal labor. They had knowledge of leverage, friction, and the properties of stone. And they had time. Scholars propose several plausible methods, none certain, but all grounded in observed capabilities of ancient engineering. One likely method involved sledges. A massive wooden platform, reinforced with bronze fittings, could distribute the stone's weight. Workers would place wooden rollers beneath the sledge, then pull it forward using ropes. Hundreds, perhaps thousands of laborers would be needed. The path from quarry to temple site slopes gently downward, which helps, but controlling a moving mass of that size on even a mild incline requires careful braking. Teams might have used friction, wedging logs behind the sledge at intervals, or employed counterweights to slow descent. Another hypothesis involves lever systems. Bronze Age engineers understood mechanical advantage. By placing long wooden beams under one edge of a stone and applying force at the far end, a small group of workers could lift an enormous weight slightly, enough to insert a support or shift the block incrementally. Repeated many times, this method could move a stone forward, albeit slowly. Evidence of lever pits, small depressions carved into bedrock where lever beams might have been anchored, appears at some ancient sites, though not definitively at Baalbek. The precision of placement is equally remarkable. The trilithon blocks align nearly perfectly, their surfaces smooth and level. This suggests careful dressing of the stone before or after placement. Workers likely used bronze saws, abrasive sand, and water to grind surfaces flat. Copper tools wear quickly against limestone, but combined with sand as an abrasive, they cut efficiently. Traces of sawing marks appear on many ancient blocks, fine parallel grooves that indicate patient, repetitive labor. Alignment required measurement. Ancient engineers used simple but effective tools. Plumb bobs ensured vertical trueness. Water-filled channels could establish level surfaces across long distances. Ropes marked with regular intervals served as measuring tapes. These methods are humble, but in skilled hands, they achieve precision within fractions of an inch. The Baalbek stones demonstrate this skill clearly. One question lingers. Why move such enormous stones at all? Smaller blocks would have been far easier to transport and assemble. The answer may lie in intention and symbolism. Monumental scale communicated power, permanence, and divine favor. A temple built with stones no other society could move proclaimed the greatness of its builders. Engineering prowess became a form of political and religious expression. The effort was immense, but the statement was clear. We may never know every detail of how the trilithon was moved, but the evidence points to human ingenuity, not mystery. The quarry marks, the abandoned stone, the understanding of levers and friction, all suggest a lost tradition of large-scale stone moving, refined over generations and then forgotten when such projects ceased. Let's turn our attention now to another marvel of ancient engineering, one built on an even grander scale, where the mysteries multiply beneath the desert sky. Part 2. Raising the Pyramids. The pyramids of Egypt rise from the Giza Plateau like geometric mountains, their slopes aligned to the cardinal directions with astonishing accuracy. The Great Pyramid, built for the pharaoh Khufu around 2500 years before the Common Era, contains an estimated 2.5 million stone blocks. Most weigh between 2 and 15 tons, though some granite blocks in the internal chambers exceed 50 tons. How these stones were lifted, placed, and fitted remains one of archaeology's most discussed questions. Quarrying the blocks was the first challenge. Most of the pyramid's mass consists of limestone, quarried locally from the Giza Plateau itself. Workers carved blocks by cutting channels into the bedrock using copper chisels and wooden wedges. Wedges, when soaked with water, expand and crack the stone along natural fissures. Alternatively, workers hammered dolerite pounders, dense igneous stones, against the limestone to pulverize and remove material. Both methods leave distinctive marks, and archaeologists have found examples of each in ancient quarries. Granite, used for the king's chamber and other interior features, came from Aswan, over 500 miles to the south. Transporting these blocks required boats. Egypt's Nile flooded annually, and during high water, boats could navigate close to construction sites. Workers likely floated granite blocks on wooden barges, then offloaded them using ramps and sledges when the water receded. Evidence of ancient harbor installations near Giza supports this reconstruction. Once stones arrived at the pyramid site, the challenge became vertical. How do you lift millions of blocks, some weighing many tons, to heights of over 400 feet? No definitive answer exists, but several plausible theories have emerged from archaeological evidence and engineering analysis. The most widely discussed method involves ramps. A long, straight ramp ascending one face of the pyramid would allow workers to drag blocks upward using sledges and ropes. As the pyramid grew taller, the ramp would extend and rise, maintaining a manageable gradient, perhaps 1 in 10. Such a ramp would eventually stretch thousands of feet and require enormous volumes of material to construct. Some researchers argue this is feasible, pointing to evidence of ramp remnants at other pyramid sites. Others propose spiraling ramps that wrapped around the pyramid's exterior. This design would be shorter and require less material, but controlling a heavy block around tight corners presents difficulties. A third theory suggests internal ramps, tunnels built within the pyramid structure through which blocks were hauled upward. French architect Jean-Pierre Houdin has championed this idea, supported by microgravimetry studies that hint at density anomalies inside the Great Pyramid, possibly indicating hollow spaces. Lever-based lifting is another possibility. Teams could use wooden levers to raise a block incrementally, inserting supports beneath it after each lift, then repeating the process. This method requires no ramps, only timber and coordinated labor. It is slow, but ancient builders had decades to complete a pyramid. Time was abundant. Counterweight systems offer a more speculative option. A large pivoting lever, weighted on one end, could lift blocks on the other. Evidence for this is thin, but the principle is sound and within the technological reach of Bronze Age engineers. Some scholars suggest combinations of methods, ramps for most blocks and levers or counterweights for the heaviest. Workforce organization was critical. Contrary to old myths, enslaved laborists did not build the pyramids. Archaeological discoveries of worker villages near Giza reveal housing, bakeries, breweries, and medical facilities. Graffiti left by work gangs, inscribed on blocks within the pyramid, reference team names and express pride in their contributions. These were skilled laborists, seasonal workers who likely participated during the Nile's flood season when agricultural work paused. Precision is another marvel. The Great Pyramid's base is level to within inches across a footprint of over 13 acres. The sides align to true north with an error of less than 1/10 of a degree. Achieving this required careful surveying. Workers probably used the stars, particularly the circumpolar stars that rotate around the celestial North Pole, to determine true north. Leveling was accomplished using water-filled trenches cut into bedrock, creating a perfectly horizontal reference plane. Fitting the blocks tightly, especially the outer casing stones which were originally smooth and white, required skill in stone dressing. Workers used bronze tools and abrasive sand to grind surfaces flat, checking fit repeatedly. The casing stones, mostly removed in later centuries for other construction, fit so precisely that gaps between them were nearly invisible. Questions remain. We do not know the exact ramp design, the ratio of skilled workers to laborists, or the detailed sequence of construction. But the evidence we have, tool marks, quarry sites, worker villages, surveying techniques, points to human capability and organization, not enigma. The pyramids stand as monuments to planning, persistence, and the accumulation of engineering knowledge over generations. As we drift further into the mysteries of stone and sand, another continent awaits, where massive walls grip mountainsides with a precision that still invites wonder. Part 3. The Walls of Sacsayhuamán. High above the city of Cusco, in the Peruvian Andes, a fortress wall curves across a hillside. The stones that form this wall fit together with such precision that centuries of earthquakes have barely shifted them. Some blocks weigh over 100 tons. Their surfaces interlock in complex polygonal patterns, each stone cut to match its neighbors exactly, edges meeting in joints so tight that not even a sheet of paper can slide between them. This is Sacsayhuamán, built by the Inca in the 15th century, and its construction methods remain only partially understood. The Inca had no written language, no wheeled vehicles, and no iron tools. They worked stone with bronze chisels, harder stone hammers, and abrasive sand. Yet they created walls that have survived 5 centuries of weathering and seismic activity in one of the world's most earthquake-prone regions. The secret lies partly in their construction technique, partly in their understanding of material properties, and partly in generations of accumulated knowledge passed from master stonemason to apprentice. The stones came from quarries several miles away. Many still bear the marks of their extraction, grooves and peck marks where workers struck the stone repeatedly with hammerstones. The Inca preferred andesite, a volcanic rock common in the region, dense and durable. To move these massive blocks without wheels or beasts of burden, they likely used a method similar to that employed at Baalbek, sledges dragged by teams of workers over log rollers-oared pathways. But the real mystery lies in the fitting. Each stone at Sacsayhuamán is unique, shaped to interlock with its neighbors in 3 dimensions. The joints curve and angle in ways that suggest the stones were fitted individually, adjusted through repeated trials. How did workers achieve such precision without modern measuring instruments? The answer appears to involve a process of scribing and grinding. One plausible reconstruction goes as follows. Workers would place a rough-cut stone near its intended position in the wall. They would then scribe its outline onto the stones already in place, marking where the new stone touched the existing surface. The new stone would be removed, and workers would grind away material along the scribed lines, creating a complementary surface. The stone would be repositioned, the fit checked, and the process repeated. Each cycle brought the surfaces closer to perfect contact. This method requires patience. Bronze tools and sand abrasives cut stone slowly. But the Inca had time and a well-organized labor system called MITA, a form of tribute labor where communities contributed workers to state projects. Thousands of labourists could be mobilized for construction, rotating in shifts, sustained by state-organized food distribution. Archaeological evidence from Inca sites shows storage facilities and administrative centers designed to support such large workforces. The polygonal style itself offers advantages. Irregular shapes distribute stress more evenly than rectangular blocks. When an earthquake strikes, the interlocking stones can shift slightly without separating, absorbing seismic energy. Modern engineers studying Sacsayhuamán have noted that the wall's flexibility, combined with its mass, makes it remarkably resilient. The Inca may not have understood seismology in modern terms, but they observed that certain wall designs survived earthquakes better than others, and they refined their techniques accordingly. Evidence of the fitting process appears in unfinished sections at various Inca sites. Some stones show partial shaping, interrupted before completion. Others display scribe marks and grinding patterns that reveal the step-by-step approach. At the quarry site of Rumacolca, massive blocks lie abandoned mid-transport, still attached to sledges made of wood and rope. These frozen moments in the construction process offer glimpses into the methods employed. One detail often overlooked is the slight inward lean of Sacsayhuamán's walls. Each course tilts back into the hillside, creating a batter that increases stability. This design choice, combined with the interlocking stones and the wall's massive weight, creates a structure that has stood while Spanish colonial buildings in Cusco, built with mortar and regularly shaped stones, crumbled in earthquakes. The Inca also understood drainage. Water seeping behind a retaining wall can build pressure and cause collapse. At Sacsayhuamán, carefully placed channels and drains direct water away from the wall's interior. These features are subtle, integrated into the stonework in ways that become apparent only upon close inspection. The attention to hydrology suggests a sophisticated understanding of the forces acting on large stone structures. Questions persist. We do not know the exact abrasives used, though quartz sand is a strong candidate. We cannot say with certainty how many workers were involved or how long construction took, though estimates suggest decades and thousands of laborious. We have no written Inca records describing the process. But the physical evidence, the tool marks, the unfinished stones, the engineering logic embedded in the wall's design, all point toward human skill refined over time. Sacsayhuamán stands as a testament to the power of empirical knowledge. The Inca learned through observation and experiment. They discovered what worked, repeated it, and passed it on. Their methods were not mysterious. They were practical, systematic, and grounded in an intimate understanding of stone. Now we turn backward in time, to a place where the very concept of monumental architecture was born, where stones were raised not to glorify kings, but perhaps for reasons we have only begun to understand. Part 4. Göbekli Tepe and the Dawn of Monuments. In the hills of southeastern Turkey, a site called Göbekli Tepe challenges many assumptions about early human societies. Here, more than 11,000 years ago, people erected massive stone pillars arranged in circular enclosures. These were not simple markers or practical structures. They were deliberate monuments, some pillars weighing 10 tons or more, carved with intricate reliefs of animals, scorpions, foxes, snakes, and birds. This happened before the invention of agriculture, before pottery, before settled villages as we typically understand them. The people who built Göbekli Tepe were hunter-gatherers, yet they organized labor and resources on a scale previously thought impossible for such societies. The site consists of multiple circular structures, each defined by a ring of T-shaped limestone pillars. These pillars were quarried from bedrock on the plateau itself. Archaeologists have found the quarries, spaces where pillars were carved out of the living rock using stone tools. The process involved pecking and grinding, striking the limestone repeatedly with harder stone hammers, especially flint, to shape the pillars. Deep grooves mark where workers carved channels to separate pillars from the bedrock. Raising these pillars required coordinated effort. Each T-shaped stone stands upright, its broad top forming a capital. To move a pillar from quarry to enclosure, workers likely used wooden sledges and ropes, dragging the stone across relatively short distances. The terrain is hilly but manageable. Erecting the pillar vertically would have required leverage. Workers probably dug a pit, tilted the pillar into it, then used ropes and wooden supports to pull it upright. Once vertical, the pit would be filled with rubble and tamped down to secure the base. The carvings on the pillars suggest more than simple construction skills. They indicate symbolic thought, narrative, and perhaps ritual significance. Foxes prowl across one pillar's surface. A vulture spreads its wings on another. These images were not incidental decorations. They were central to the site's purpose, whatever that purpose was. Göbekli Tepe appears to be a ceremonial center, a place where groups gathered for reasons we can only infer: feasting, ritual, social bonding, perhaps marking seasonal events or astronomical observations. The implications for understanding ancient engineering are profound. If hunter-gatherers could organize the labor needed to build Göbekli Tepe, then the capacity for large-scale construction predates agriculture. This challenges the older narrative that monumental architecture required settled farming communities to generate surplus food and stable populations. Instead, Göbekli Tepe suggests that the desire to build, to create shared spaces of significance, may have driven social organization, possibly even contributing to the later development of agriculture as a way to sustain the gatherings these sites enabled. Engineering knowledge at Göbekli Tepe was necessarily simpler than in later civilizations, but it was present. Workers understood leverage and balance. They knew how to quarry stone efficiently using the tools available. They could transport heavy objects and erect them securely. These are foundational skills, the bedrock upon which later engineering traditions would build. Göbekli Tepe represents an early chapter in humanity's long relationship with stone. One aspect of the site remains particularly intriguing. After a period of use, the circular enclosures were deliberately buried. Workers filled them with rubble and soil, preserving the pillars and carvings beneath the earth. Why this was done is unknown. Perhaps the site lost its ritual significance. Perhaps burying the old enclosures was itself a ritual act, a way of closing one chapter before beginning another. Newer enclosures were built nearby, then they too were buried. This pattern of construction, use, and burial continued for centuries. The site's discovery was relatively recent, excavations beginning in the 1990s. As archaeologists continue to uncover more of Göbekli Tepe, the picture becomes richer but not necessarily clearer. Each new pillar, each new carving, adds detail but also raises questions. The site does not fit neatly into established categories. It is a monument built by mobile people, a ceremonial center before cities, an expression of symbolic thought before writing. From an engineering perspective, Göbekli Tepe demonstrates that the core challenges of monumental construction, quarrying, transport, erecting pillars, and organizing labor, were solved much earlier than once believed. The methods were straightforward but effective. The tools were stone, but in skilled hands they shaped stone. The workforce was probably small compared to later pyramid building projects, but it was sufficient for the task. As we contemplate these ancient pillars standing in their buried circles, we are reminded that the human impulse to build, to mark the landscape with intention and effort, runs deep. Engineering arose not just from necessity but from aspiration, from a desire to create something that endured, something that spoke to others across time. Let us move forward now, across millennia, to another puzzle of precision and scale, where the movement of water through stone channels sustained entire civilizations. Part 5. Lost Waterworks and Forgotten Hydrology. Water is the foundation of civilization. Cities cannot grow without reliable sources of fresh water, and agriculture cannot flourish without irrigation. Ancient engineers understood this deeply. They constructed aqueducts, reservoirs, canals, and canal systems that rival modern infrastructure in scope and ingenuity. Yet many of these systems are now lost, collapsed, or buried, their engineering principles only partially recovered through archaeology and careful study of surviving remnants. The canals of Persia, underground channels that tap into groundwater and carry it across vast distances, represent one of the most sophisticated ancient water systems. A canal begins with a mother well dug into an aquifer, sometimes hundreds of feet deep. From this well, a gently sloping tunnel extends toward the settlement or farmland requiring water. The slope is critical, typically just a few feet per mile, enough to allow water to flow by gravity but not so steep that the channel erodes. Vertical shafts punctuate the tunnel at regular intervals, providing ventilation for workers during construction and access for maintenance. Digging a canal required precision surveying. Workers had to maintain the correct gradient over distances that could stretch for miles. Too steep and water would flow too fast, eroding the channel. Too shallow and water would stagnate. Ancient engineers likely used simple but effective leveling methods, possibly weighted strings or water-filled tubes, to check the grade as they dug. The shafts, spaced every 50 to 100 feet, were dug first. Then workers excavated the connecting tunnel from the bottom of each shaft, meeting in the middle with remarkable accuracy. Many canals in Iran, Afghanistan, and other parts of the Middle East and Central Asia are still in use, some over 2,000 years old. Their longevity speaks to the quality of their construction. The underground design protects the water from evaporation, crucial in arid climates, and keeps it cool. Maintenance is continuous, sediment must be cleared, and collapses repaired, but the basic system endures. Roman aqueducts are perhaps the most famous ancient water systems, and with good reason. The Romans built aqueducts across their empire, from Spain to Syria, carrying water from distant springs and rivers to cities and towns. The Aqua Claudia in Rome, completed in the 1st century of the Common Era, stretched over 40 miles, much of it underground or in low channels, but culminating in dramatic arcaded sections where the channel crossed valleys on towering stone arches. The engineering challenge in aqueduct construction was maintaining a consistent downward slope. Roman engineers achieved this using a tool called a corybates, a long wooden frame with a water-filled groove along its top. By ensuring the water level was even across the groove, they could establish a horizontal reference, then build the channel at a slight angle from that reference. The gradient of Roman aqueducts was typically very gentle, often just a few inches per mile, allowing water to flow steadily without excessive speed. Arched bridge sections, the iconic image of Roman aqueducts, served a specific purpose. Where the terrain dropped into a valley, engineers had two choices: follow the contour, extending the aqueduct miles out of the way, or bridge the gap. Arches allowed them to maintain the gradient directly across the valley. The physics of the arch, each stone in compression, pushing against its neighbors, created a stable structure capable of supporting the weight of the water channel above. Roman engineers refined the arch over centuries, learning through trial and error how to proportion the curve, how thick to make the supports, how deep to set the foundations. Some aqueducts included sophisticated features like settling tanks, where water slowed and sediment dropped out, keeping the main channel clear. Others had distribution systems with multiple branches, sluice gates to control flow, and even pressure pipes where the terrain required water to flow uphill briefly. Inverted siphons, where water descended into a valley and rose again on the other side through sealed lead or stone pipes, demonstrate an understanding of hydraulic pressure. The Romans knew that water in a closed system would rise to the level of its source, and they used this principle to cross valleys without building towering arches. In the Americas, ancient civilizations developed their own water management systems. The Nazca people of coastal Peru, living in one of the driest places on Earth, built puquios, underground aqueducts similar in concept to canats. These spiral stone-lined channels tapped into aquifers and brought water to the surface. Some puquios are still functional, maintained by local communities using traditional methods. The engineering knowledge required to build them in a desert environment, where trial and error could mean the difference between survival and catastrophe, indicates careful observation of hydrology and skilled stonework. The ancestral Puebloans of the American Southwest created irrigation systems that channeled seasonal runoff from mesas to agricultural fields below. Check dams, small stone barriers built across gullies, slowed water flow and encouraged infiltration, recharging groundwater and preventing erosion. These systems were adapted to a landscape of flash floods and long droughts, designed to capture every drop of precious water. Maya cities in the lowlands of Central America faced a different challenge: seasonal rainfall but no permanent rivers. They built reservoirs lined with plaster to catch and store rainwater during the wet season. The plaster, made from lime and fine sand, was waterproof and durable. Some reservoirs held millions of gallons, sustaining cities through the dry months. The construction of these reservoirs required understanding soil permeability, calculating volume, and managing the chemistry of plaster production, all practical engineering knowledge developed through generations of experience. Many ancient water systems are now lost, buried under sediment, dismantled for building materials, or simply abandoned as populations shifted. Archaeologists rediscover them using a variety of methods: ground-penetrating radar, aerial photography that reveals subtle changes in vegetation or soil color, and old maps or texts that hint at locations. Each rediscovered aqueduct or canal adds to our understanding of how ancient societies managed their most vital resource. The engineering principles behind these systems are not mysterious. Gravity, slope, and the properties of water in motion are constant. What varied was the ingenuity with which ancient engineers applied these principles, adapting to local conditions, available materials, and the scale of need. Their waterworks stand, where they still stand, as monuments to practical problem-solving and long-term planning. We pause here, the flow of water through stone, a quiet reminder of the patient work that sustained cities and fields, work that continues in some places, unbroken for millennia. Part 6. Precision in stone. Ancient builders achieved remarkable precision with tools we might consider primitive. The granite blocks inside the Great Pyramid's King's Chamber fit so closely that gaps measure less than 1/50th of an inch. The floors of Roman temples lie perfectly level across expanses of marble. Inca walls meet in joints invisible to the naked eye. How did ancient masons achieve such accuracy without modern measuring instruments or power tools? The answer lies in patience and systematic method. Stone surfaces were dressed using a process of progressive refinement. Workers began with rough shaping, using hammerstones or bronze chisels to remove large amounts of material quickly. This established the approximate form. Next came finer work, smaller tools striking more carefully, bringing surfaces closer to the desired plane. The final stage involved grinding with abrasive materials. Abrasives were key. Sand, particularly quartz sand, is harder than most building stones. When workers rubbed a block of harder stone back and forth across a softer surface with wet sand between them, the sand particles cut microscopic grooves, gradually wearing away high spots. Given enough time and consistent pressure, this method produces surfaces flat to within thousandths of an inch. The technique is simple but labor-intensive. A single surface might require days of grinding. Testing flatness required reference surfaces. Ancient masons likely used master blocks, stones already ground perfectly flat, which they placed against surfaces being worked. Any gaps revealed high or low spots. Workers marked these areas and continued grinding. Another method involved coating a test surface with pigment, pressing it against the workpiece, and noting where color transferred. Areas that picked up pigment were high and needed more work. Right angles presented a similar challenge. The Romans used large bronze squares, tools shaped like the letter L with precisely formed 90-degree angles. Masons held these against corners being cut, checking for gaps. Egyptian builders may have used knotted ropes formed into triangles with sides in a 3:4:5 ratio, which automatically creates a right angle. This mathematical relationship, known long before Pythagoras, gave workers a reliable method for checking squareness. Straightness along long distances required sighting techniques. Workers stretched strings taut between fixed points, creating a reference line. Any deviation in the stone surface from this line could be seen and marked. For very long structures, they used a series of aligned stakes or posts, sighting down the line to ensure all points remained collinear. These methods sound crude, but they work. Modern stonemasons using traditional techniques achieve results indistinguishable from those of ancient builders. Circles and curves demanded different approaches. For circular structures, workers established a center point and used a rope of fixed length as a compass, scribing an arc on the ground or stone surface. Cutting a curved surface required patient chiseling, constantly checking progress against the marked line. Some ancient sites show compass marks still visible in the stone, evidence of the layout process. The tools themselves were carefully made. Bronze chisels were forged and sharpened to specific angles depending on the stone being worked. Soft limestone required different edge geometry than hard granite. Experienced masons knew which tool to use for each material and task. They maintained their tools constantly, resharpening edges worn dull by contact with stone and sand. One often overlooked aspect of precision work is the mason's eye. After years of practice, skilled workers could judge flatness and straightness visually with surprising accuracy. They felt the stone surface with their hands, detecting minute irregularities by touch. This sensory expertise, combined with systematic checking using tools, enabled the precision we observe in ancient structures. Temperature affected the work. Stone expands slightly when heated and contracts when cooled. Masons working outdoors had to account for these changes, particularly on large projects where blocks cut in summer might be placed in winter. The solution was to work stone slightly oversized, then make final adjustments after placement when thermal expansion stabilized. Let us consider now the question of moving these precisely shaped stones without damaging their carefully prepared surfaces. Part 7. Transport and Logistics. Moving stone was as much a logistical challenge as an engineering one. A single large block required not just physical force but planning, coordination, and infrastructure. Ancient builders developed sophisticated systems for transport, adapting methods to terrain, distance, and available resources. Sledges formed the foundation of most transport systems. These were heavy wooden platforms, reinforced with cross braces and fitted with runners shaped to slide across the ground. The stone block rested on the sledge, lashed down with ropes to prevent shifting. Teams of workers, sometimes hundreds for the largest loads, pulled the sledge using ropes attached to its front. Archaeological evidence from Egypt shows such sledges in tomb paintings, workers hauling a colossal statue while one person pours liquid in front of the runners. That liquid, probably water or oil, reduced friction dramatically. Experiments by physicists have demonstrated that wetting sand in front of sledge runners cuts the force needed to pull a load by nearly half. The moisture binds sand particles together, preventing them from piling up in front of the runners and creating a firmer surface. This simple technique made enormous differences in efficiency. Rollers offered another method. Wooden logs placed under a sledge allowed it to roll rather than slide. As the sledge moved forward, workers picked up rollers from behind and carried them to the front, maintaining a continuous path. This method works well on flat terrain but becomes difficult on slopes where controlling the load requires constant braking. Some researchers suggest rollers were used for shorter distances or in combination with sledges. Roads built specifically for transport appear at several ancient sites. Near the Giza pyramids, archaeologists found remnants of constructed causeways, wide paths paved with stone or packed clay, running from quarries to building sites. These roads provided smooth, predictable surfaces for moving blocks. Their construction was itself a major project, but the investment paid returns in faster, safer transport of materials. River transport solved the problem of moving materials over long distances. Egypt's pyramids and temples benefited from the Nile's annual flood cycle. During high water, boats could navigate channels close to construction sites. Granite from Aswan, limestone casing stones from Tura, both traveled hundreds of miles by river. Barges were built specifically for stone transport, massive flat-bottomed vessels that could carry multiple blocks. Loading and unloading required ramps and coordinated timing with water levels. In mountainous regions, transport became more complex. The Inca moved stones uphill along mountain paths too steep and narrow for sledges. Evidence suggests they used a combination of methods. Smaller stones might be carried by hand or on backs, secured with ropes. Larger blocks required teams using levers and fulcrums to shift them incrementally. Some researchers propose rolling stones on logs along prepared tracks, though this remains speculative. Organizing the workforce was crucial. Someone had to plan routes, coordinate teams, arrange food and water for workers, maintain equipment, and solve problems as they arose. Evidence of administrative structures appears at major ancient building sites. At Giza, papyri fragments describe delivery schedules for supplies and assignments of work gangs to specific tasks. This bureaucratic infrastructure, often invisible in the finished monument, made large-scale construction possible. Timing mattered. In Egypt, construction likely intensified during the inundation season when agricultural work ceased and labor could be redirected to building projects. In other regions, seasonal patterns of weather, harvest, and religious observance influenced construction schedules. Builders worked within these rhythms, adapting their plans to available labor and conditions. Damage control required attention. Moving a precisely shaped stone risked chipping corners or cracking surfaces. Workers likely wrapped blocks in protective materials, possibly woven reed mats or layers of rope, cushioning the stone during transport. Final finishing often occurred after placement, allowing workers to repair any damage and ensure tight fits between adjacent blocks. Now we turn to the question of lifting, of raising these massive stones from ground level to their final positions high in walls and pyramids. Part 8. Methods of lifting. Raising stone vertically challenged ancient engineers more than any other aspect of construction. Gravity pulls relentlessly downward, and every foot of height multiplies the difficulty. Yet ancient builders lifted granite blocks weighing 50 tons to heights of hundreds of feet. They did so without cranes, without pulleys as we know them, and without steel cables. Understanding their methods requires thinking through the physics of leverage and the clever use of simple machines. Ramps remain the most widely accepted lifting method. A gently sloping incline allows workers to pull a block upward using the same sledge and rope techniques employed for horizontal transport. The shallower the ramp's angle, the less force required, but the longer the ramp must be. A 10-degree slope requires a ramp 10 times longer than the height to be reached. For a structure like the Great Pyramid, this presents challenges. A straight ramp reaching the pyramid's apex would stretch over a mile long. This realization led scholars to propose alternative ramp designs. Spiral ramps wrapping around the pyramid's exterior solve the length problem, but introduce the difficulty of turning corners with heavy loads. Zigzag ramps switching back and forth up one face offer another solution. Internal ramps built into the structure itself avoid external construction but require careful integration with the pyramid's design. Evidence for ramps exists at several sites. The Pyramid of Meidum in Egypt shows remnants of a large supply ramp. Unfinished pyramids preserve ramp structures built against their faces. These discoveries confirm that ramps were used, though exactly which configurations served different projects remains uncertain. Likely, builders adapted designs to specific circumstances. Levers provided an alternative or supplement to ramps. A long wooden beam placed under one edge of a stone becomes a lever. Workers pushing down on the far end lift the stone slightly. This small lift allows others to insert packing material beneath the block. When the lever is removed, the stone rests higher than before. Repeating this process from different sides, the stone gradually rises. This method is slow. Lifting a block 10 feet might require hundreds of lever cycles, but it demands less infrastructure than ramps and works in confined spaces. Some researchers suggest levers were used for final positioning or for adjustments after blocks reached their approximate location via ramps. The two methods, ramps for bulk lifting and levers for precision, may have worked together. A variation involves lever platforms. Construct a wooden platform next to the rising wall. Use levers to raise a block onto the platform. Build another platform on top of the first. Lever the block onto the second platform. Continue upward in stages. This creates a temporary tower beside the permanent structure, allowing blocks to ascend in steps. Evidence for such platforms is scarce, as they would have been dismantled after use, but the method is practical and within ancient capabilities. Counterweights offer intriguing possibilities. A large pivoting arm, weighted on one end, could lift loads on the other. The shaduf, a water lifting device used in ancient Egypt, employed this principle. Scaling it up to lift stone blocks is conceptually straightforward, though engineering a structure strong enough to handle multi-ton loads presents challenges. Some researchers propose that such devices existed but left little archaeological trace because they were made entirely of wood and rope. Pulleys, in the modern sense of grooved wheels over which rope runs, appear later in history. However, simple rope over beam arrangements, where rope passes over a wooden beam to change direction, were certainly available. These don't reduce the force needed but do allow workers to pull downward using their body weight rather than pulling horizontally or upward. This is mechanically advantageous and may have been exploited. Combinations of methods seem most likely. Initial lifting via ramps brought blocks to intermediate heights. Levers handled final positioning and adjustment. Rope and beam systems assisted in controlling descent into place. Ancient builders were pragmatic, using whatever worked for the specific situation they faced. Flexibility and adaptation, not rigid adherence to a single method, characterized their approach. One detail often mentioned is the absence of mortar in many ancient structures. Blocks rested directly on one another, held by weight and friction. This meant each block had to fit precisely before being released. Lifting and lowering stones multiple times to check fit was part of the process. Workers might raise a block, find the fit unsatisfactory, lower it, adjust grinding, and raise it again. This iterative fitting consumed time but ensured the quality we observe. As we rest here, the image of stones rising slowly against the sky, we recognize the patience embedded in these structures, the accumulated effort of countless lifts and adjustments, each small motion contributing to the monumental whole. Part 9. Quarrying techniques. Before stones could be moved or lifted, they had to be freed from the earth. Quarrying was the first and perhaps most fundamental challenge of ancient construction. Different stones required different approaches, and ancient quarrymen developed specialized techniques for each material they encountered. Limestone, used extensively in Egypt and elsewhere, splits relatively easily along natural bedding planes. Workers identified these planes and exploited them. They carved channels around a block using copper or bronze chisels, isolating it on 3 or 4 sides. Wooden wedges were driven into cracks at the base. When soaked with water, these wedges expanded, generating tremendous pressure that fractured the stone along its weakest plane. The block could then be pried loose and removed. Some quarries show a different method. Workers drilled or cut a series of holes along a line, then inserted wedges into each hole simultaneously. When struck together, these wedges created multiple fracture points, causing the stone to break cleanly along the intended line. This technique appears in both ancient Egypt and Greece, evidenced by rows of wedge holes still visible in abandoned quarry faces. Granite presented greater difficulty. This igneous rock has no consistent grain and resists chiseling. Egyptian quarrymen developed methods using dolerite, an extremely hard stone. They fashioned dolerite balls, roughly the size of melons, and pounded them repeatedly against granite surfaces. The impact pulverized the granite bit by bit. It was exhausting work, but effective. Archaeologists have found dolerite pounders scattered throughout granite quarries at Aswan, worn smooth from use. For creating channels in granite, workers might have used a combination of pounding and abrasive drilling. Copper tubes rotated with sand and water acting as the cutting agent could bore deep holes. A series of holes along a line could then be connected by pounding, creating a channel. Evidence of this technique appears in unfinished granite workpieces where drill holes remain visible. Fire setting, a method documented in later Roman mining, may have been used in some ancient quarries. Workers built fires against the rock face, heating it intensely, then doused the hot stone with cold water. The thermal shock caused the surface to crack and spall. Repeated heating and cooling could fragment rock more quickly than pounding alone. Evidence for fire setting is difficult to confirm archaeologically, as it leaves subtle traces, but some researchers point to discoloration patterns on quarry walls as possible indicators. Quarry sites themselves reveal much about ancient methods. At Baalbek, the unfinished stone of the south shows the process frozen mid-work. Channels surround it on 5 sides, cut to depths of several feet. The stone remains attached to bedrock only at its base. Had work continued, that final connection would have been severed, perhaps using wedges, and the stone levered free. The abandonment of this block teaches us that even experienced quarrymen faced challenges that sometimes proved insurmountable. Organization of quarry work required planning. Teams specialized in different tasks. Some cut channels, others drove wedges, still others prepared tools or managed transport of freed blocks. Supervisors marked stones with symbols indicating their destination or intended use. At some Egyptian quarries, inscriptions name the work gangs and their leaders, providing glimpses of the human organization behind the technical work. Unfinished blocks offer valuable evidence. At Aswan, numerous partially worked granite pieces lie scattered, abandoned for reasons we can only guess. Some show cracks that developed during extraction, rendering them unusable. Others may have been left when priorities shifted or when a quarry was exhausted of suitable stone. These fragments display tool marks clearly, showing exactly how workers approached their task. Quality control mattered. Not every stone was suitable for construction. Quarrymen learned to read rock, identifying flaws, inclusions, and weaknesses that might cause problems later. They rejected blocks with cracks or mineral intrusions. This selection process meant that much quarried material never left the site, remaining as waste debris that now helps archaeologists understand ancient standards. The journey from bedrock to building block began in these quarries, where skill and strength transformed living stone into components for monuments that would outlast their makers by millennia. Part 10. Alignment and Astronomy. Many ancient structures exhibit precise alignments with celestial phenomena. The Great Pyramid's sides align to the cardinal directions within a fraction of a degree. Stonehenge's axis points toward the midsummer sunrise. Temple doorways frame specific stars at significant dates. These alignments were not accidental. They resulted from careful observation and systematic measurement, demonstrating that ancient builders possessed sophisticated knowledge of celestial mechanics. Determining true north required patience and clear skies. Egyptian astronomers likely used circumpolar stars, those that never set below the horizon as they rotate around the celestial pole. By observing two positions of a star, one rising and one setting, and bisecting the angle between them, observers could establish a north-south line. Another method involved tracking the shadow cast by a vertical pole throughout the day. The shadow at noon points true north in the northern hemisphere. Repeating these observations over multiple days and averaging the results increased accuracy. The Merkit, an Egyptian surveying tool, consisted of a plumb line hung from a notched bar. When aligned with a sighting cord held by an assistant, it allowed observers to establish straight lines and angles with precision. Pairs of Merkits could define a north-south line based on stellar observations. Once established, this line served as a reference for laying out foundations. Solar alignments presented different opportunities. Many cultures marked solstices, the longest and shortest days of the year, when the sun reaches its extreme northern or southern rising position. Observing these positions over years allowed builders to mark them permanently in architecture. A doorway framing the winter solstice sunrise created a dramatic annual event, linking the structure to cosmic rhythms. Lunar alignments appear in some monuments. The moon's rising and setting positions vary over a cycle of approximately 19 years, reaching extreme positions called major and minor standstills. Some researchers argue that certain stone circles in Britain mark these lunar extremes, suggesting multi-generational observation programs. This remains debated, as establishing such alignments requires statistical analysis of numerous sightlines and careful consideration of alternative explanations. The purpose of these alignments varied by culture and structure. Some were clearly calendrical, marking agricultural seasons or religious festivals. Others may have been symbolic, connecting earthly structures to heavenly patterns. Still others might have served practical purposes, such as determining when to plant crops or prepare for seasonal floods. Separating these functions is difficult, as they often overlapped. Precision in alignment required not just astronomical knowledge but also practical surveying skill. Once a direction was established by observation, maintaining that bearing across hundreds of feet of construction demanded careful work. Sighting stakes set at intervals allowed workers to check their progress. String lines stretched between stakes defined edges and corners. Any deviation could be detected and corrected before it compounded. The Great Pyramid's alignment demonstrates the achievable accuracy. Its base forms a square with sides averaging 756 feet in length. The difference between the longest and shortest sides is less than 2 inches. The sides align to true north with an error of about 3 arc minutes, roughly 1/20th of a degree. This precision, achieved without magnetic compasses or telescopes, speaks to careful application of basic observational techniques. Some alignments may be coincidental. With enough structures built in various orientations, some will inevitably align with celestial events by chance. Archaeoastronomers must distinguish intentional alignments from statistical accidents. This requires examining multiple features of a site, considering cultural context, and avoiding cherry-picking data that supports a desired conclusion. What remains clear is that ancient builders paid attention to the sky. They incorporated their observations into their architecture, creating structures that connected Earth to heavens. The methods they used, patient observation, careful measurement, and practical geometry, were accessible to any society willing to invest the time and effort. Part 11. Labor and social organization. Behind every ancient monument stood not just engineering knowledge but organized labor. Moving millions of stones, feeding thousands of workers, coordinating tasks across years or decades, these required administrative systems as sophisticated as the technical methods employed. Understanding ancient construction means understanding how societies mobilized and sustained the human effort necessary. The workforce for major projects numbered in the thousands. Estimates for the Great Pyramid suggest 10,000 to 20,000 workers over 2 decades, though these numbers remain uncertain. Not all were laborious. The workforce included stonecutters, surveyors, toolmakers, rope makers, carpenters, and water carriers. Administrators tracked supplies, assigned tasks, and resolved disputes. Scribes recorded deliveries and work progress. The entire operation resembled a small city focused on a single purpose. Feeding this workforce required agricultural surplus and distribution systems. At Giza, archaeological evidence reveals bakeries, breweries, and butchering facilities. Workers received rations of bread, beer, and occasionally meat. The quantities needed were enormous. Estimates suggest over 4,000 loaves of bread daily just for the primary workforce. This food had to be grown, processed, transported, and distributed reliably. Failure in the supply chain could halt work and threaten the project. Housing for workers appears at many ancient sites. At Giza, a workers' village provided simple but functional accommodation. At Amarna, the short-lived capital of Akhenaten, a similar village housed construction workers. These settlements included not just sleeping quarters but also spaces for food preparation, tool storage, and medical treatment. The presence of medical care, evidenced by healed fractures and surgical interventions in skeletal remains, indicates that workers' welfare received attention. Labor organization followed hierarchical structures. Work gangs, groups of perhaps 20 men, formed the basic unit. Multiple gangs constituted a crew. Multiple crews formed a division. Each level had leaders responsible for their section's productivity. Graffiti inside pyramids records gang names, often colorful, such as Friends of Khufu or Drunkards of Menkaure. These names suggest camaraderie and perhaps competition between groups. Motivation of workers remains a subject of discussion. Old theories of slave labor have been largely discredited. Evidence suggests a mixture of permanent skilled workers and temporary conscripted labor. The conscripts, probably farmers during agricultural off-seasons, fulfilled labor obligations to the state. In return, they received food, shelter, and participation in a project of national and religious significance. Pride in the work, social obligation, and practical survival all likely played roles. Seasonal patterns influenced work schedules. In Egypt, the Nile's annual flood made farming impossible for several months, but also facilitated stone transport by water. Construction likely intensified during this period. In other regions, different seasonal factors applied. The Inca MITA system rotated labor obligations, ensuring fresh workers while allowing communities to maintain their own agricultural and social activities. Technical training was necessary. Skilled tasks like stone cutting, surveying, and carpentry required years of apprenticeship. Master craftsmen passed knowledge to younger workers through direct instruction and observation. This ensured continuity of technique across generations. Some workers specialized in particular aspects, becoming experts in narrow but essential skills. Accidents happened. Construction sites are inherently dangerous, especially when moving multi-ton stones. Skeletal remains from worker cemeteries show injuries consistent with construction accidents, crushed bones, fractures, and trauma. That workers received medical care and burial with some dignity suggests they were valued, not disposable. Society invested in these individuals and their skills. Religious and ceremonial aspects surrounded major projects. Foundation rituals, completion ceremonies, and ongoing religious observances marked construction milestones. Workers participated in these events, connecting their labor to cosmic and divine purposes. The structures they built were not merely functional but sacred, and their role in creating sacred space held meaning. As we pause here, we recognize that stone and engineering knowledge alone could not build monuments. Human organization, sustained effort, and shared purpose transformed individual blocks into enduring structures. Part 12. Stone dressing and surface finishing. The final appearance of ancient structures depended as much on surface finishing as on construction itself. Raw quarried stone, rough and irregular, had to be transformed into smooth, uniform surfaces that fit precisely and presented the desired aesthetic. This finishing work represented a significant portion of total labor and required specialized skills distinct from quarrying or transport. The process began with rough dressing at the quarry. Workers removed obvious protrusions and shaped blocks to approximate dimensions, reducing weight for transport. This rough work left surfaces uneven, covered with tool marks and irregularities. Final finishing occurred after placement, allowing masons to adjust individual blocks to achieve perfect fit with neighbors. For limestone, bronze chisels were the primary finishing tool. Masons held the chisel at specific angles against the stone surface and struck it with wooden or stone mallets. Each blow removed a small chip. Working systematically across the surface, they gradually reduced high spots and smoothed irregularities. The angle of the chisel determined the size of chips removed. Shallow angles took fine cuts for detailed work, while steeper angles removed material more aggressively. Different chisel types served different purposes. Point chisels, with pyramid-shaped tips, broke down rough surfaces quickly. Flat chisels, with straight cutting edges, smoothed areas and created level planes. Toothed chisels, with serrated edges, removed material in controlled strips, leaving characteristic parallel grooves visible on many ancient surfaces. These grooves often remain as evidence of the finishing process, intentionally left in less visible areas or covered by now lost plaster. Granite required different approaches due to its hardness. Bronze tools dulled quickly against granite. Instead, masons used abrasion. They rubbed harder stones, often quartzite or dolerite, across granite surfaces with sand and water. The sand particles, caught between the rubbing stone and the work surface, acted as the cutting agent. This method was slow but effective. A single surface might require weeks of grinding to achieve smooth flatness. Polishing created the highest quality finishes. After grinding a surface smooth, workers continued with progressively finer abrasives. Coarse sand gave way to fine sand, then to powdered materials like crushed quartz or emery. Each stage removed scratches left by the previous one, gradually creating surfaces that reflected light. The red granite sarcophagus in the Great Pyramid's King's Chamber displays this level of finish, its surfaces polished to near mirror quality. The outer casing of pyramids received exceptional attention. Original casing stones, mostly removed in later centuries, were fine white limestone polished smooth. These stones fit so precisely that gaps between them measured less than 1/50th of an inch. Each casing stone was dressed after placement, ensuring continuity across joints. The result was a smooth, gleaming surface that caught sunlight brilliantly, making pyramids visible for miles. Measuring tools ensured uniformity. Straight edges, long bars of wood or metal with perfectly straight sides, checked surface flatness. Squares verified right angles at corners. Levels, probably water-filled troughs or plumb lines, ensured horizontal surfaces. Masons checked their work constantly, testing with these instruments and making adjustments where needed. Some finishing work created deliberate textures. Greek temples often feature column drums with drafted margins, smooth bands around edges with rougher centers. This technique indicated quality, showing that masons had the skill to smooth stone but chose to leave texture for aesthetic effect. Other surfaces received pecked finishes, uniform patterns of small indentations covering the stone, creating visual interest and improving grip on walking surfaces. Evidence of the finishing process survives in unfinished structures. The small temple at Medinet Habu in Egypt preserves column surfaces in various stages of completion. Some areas show rough quarry faces. Others display parallel grooves from toothed chisels. Still others are partially smoothed. This frozen progression reveals the sequence of work, from rough to refined. Tool marks themselves tell stories. The direction of chisel strokes indicates whether masons worked right-hand or left-handed. The spacing of marks suggests tool size. Variations in technique between different sections hint at multiple workers or teams with slightly different methods. Close examination of these traces brings ancient craftsmen to life, their individual techniques and work rhythms preserved in stone. Finishing work extended to carved details. Hieroglyphs, reliefs, and decorative elements required specialized skills. Carvers worked with small chisels and fine abrasives, removing stone in tiny increments to create precise forms. The depth and quality of carving varied with the stone's visibility and importance. Hidden surfaces received minimal attention. Prominent facades received hours of careful work per square foot. Let us move now to consider how these finished stones, precisely shaped and smoothly dressed, were fitted together into structures designed to endure. Part 13. Joinery and structural stability. Ancient builders understood that stability came not from mortar but from careful fitting and weight distribution. Many of the most enduring ancient structures use no binding agent between stones. Blocks rest directly on one another, held by gravity and friction. This dry stone construction required precise joinery and thoughtful structural design to resist earthquakes, weathering, and the passage of millennia. The key principle was load distribution. Weight pressing down on stones creates friction between surfaces, preventing lateral movement. The greater the weight, the stronger this frictional grip. Massive stones, despite seeming harder to work with, actually contributed to structural stability through sheer mass. Ancient builders exploited this, often placing their heaviest stones at the base and in critical load-bearing positions. Joints between stones were shaped to maximize contact area. Flat surfaces meeting across their full extent create more friction than point contacts. This required the precision finishing discussed earlier. Even small gaps or irregularities reduced contact area and weakened the joint. Masons tested fit repeatedly, marking high spots, removing them, and testing again until surfaces met fully. Some structures employed interlocking joints. Stones cut with protruding tabs that fit into corresponding recesses in adjacent blocks created mechanical connections. The Inca used this technique extensively, shaping stones with complex three-dimensional profiles that locked together like puzzle pieces. This prevented lateral sliding even in earthquakes, as movement in any direction encountered resistance from the interlocking geometry. Metal clamps and dowels reinforced joints in Greek and Roman construction. Iron or bronze clamps, shaped like capital I beams, were set into channels cut across the joint between two blocks. Molten lead poured around the clamps secured them in place. These clamps prevented blocks from sliding apart. Vertical dowels, metal pins set into aligned holes in stacked blocks, prevented vertical displacement. Evidence of clamp and dowel use appears as empty channels and holes in ancient structures, the metal long since stolen for reuse. Corbelling created arches and vaults without true arch construction. Each course of stones projected slightly beyond the one below, gradually closing a gap or spanning a space. The projections remained small enough that the weight of upper courses held lower ones in place through friction. Corbelled structures appear in many ancient cultures, from Mycenaean tombs to Maya palaces, demonstrating independent discovery of this stable technique. True arches distributed loads differently. Stones cut as wedges, narrow at the bottom and wide at the top, formed a curve when placed side by side. The wedge shape meant that weight pressing down forced stones together rather than allowing them to fall. The keystone, the central wedge at the arch's top, locked the entire structure. Once in place, an arch became self-supporting, even strong enough to carry additional weight above. Romans mastered arch construction, using it for bridges, aqueducts, and monumental buildings. They understood that arch thrust, the outward force at the arch base, required massive supports or buttressing. Their structures incorporated thick walls and substantial foundations to resist these forces. Mathematical understanding of force distribution, though not expressed in modern equations, guided their proportions through experience and tradition. Foundation design was critical. Even perfectly fitted stones fail if the ground beneath them shifts. Ancient builders addressed this through careful site preparation. They removed loose soil, sometimes excavating to bedrock. Where bedrock was too deep, they created artificial foundations using compacted layers of gravel, sand, and rubble. Some sites show evidence of pile foundations, wooden posts driven into soft ground to create stable bearing surfaces. Earthquake resistance required specific features. The Incas' interlocking stones and slightly inward-leaning walls helped structures flex during seismic activity without collapsing. Greek temples used column drums, individual cylindrical stones stacked to form columns, rather than monolithic shafts. During earthquakes, these drums could shift slightly without breaking, dissipating energy. Wooden dowels connecting drums allowed movement while preventing collapse. Drainage protected structures from water damage. Channels cut into paving stones directed rainwater away from foundations. Gutters and downspouts prevented water from pooling against walls. Underground drains, often sophisticated systems of stone channels, carried groundwater away from beneath structures. Many ancient buildings failed not from structural defects but from water infiltration undermining foundations or eroding materials. Expansion joints, deliberate gaps between sections of large structures, accommodated thermal expansion and ground settlement. Without these, differential movement could crack solid construction. Some ancient builders incorporated such joints, though whether by design or accident remains uncertain in many cases. The longevity of ancient structures testifies to sound engineering principles. Buildings that have survived earthquakes, wars, and millennia of weathering demonstrate that their builders understood structural mechanics deeply, even if they could not articulate that understanding in modern terms. Their knowledge came from observation, experience, and the accumulation of lessons learned from both successes and failures. We rest here amid fitted stones, each one bearing weight and transferring forces according to principles discovered through patient trial and refinement. Part 14. Tools and their evolution. The tools available to ancient builders defined what they could achieve. From simple stone hammers to sophisticated bronze instruments, each tool represented accumulated knowledge about materials, forces, and efficient work methods. Understanding ancient tools helps us appreciate both the limitations builders faced and the ingenuity with which they overcame them. The earliest construction tools were stones themselves. Hard stones shaped softer ones through percussion. Flint, quartzite, and granite became hammers and pounders. Workers gripped these naturally shaped stones or hafted them to wooden handles for better leverage. Thousands of such stone tools litter ancient quarry sites, worn smooth from use, sometimes cracked from repeated impacts. Copper appeared early in human history, soft but workable. Ancient smiths hammered copper into chisels and saws. Pure copper dulls quickly against stone, but it served for softer materials like limestone and sandstone. Egyptian workers used copper tools extensively, sharpening them frequently as edges wore. The effort of constant resharpening was offset by copper's availability and ease of working. Bronze, an alloy of copper and tin, transformed tool making. Harder than pure copper, bronze held an edge longer and withstood greater impact forces. Bronze chisels could cut limestone efficiently. Bronze saws, used with abrasive sand, could even cut granite. The discovery of bronze represented a significant technological advancement, enabling more ambitious construction projects. Tool design evolved through experience. Early chisels were simple wedges. Later versions featured reinforced sockets for handles, reducing breakage. The angle of the cutting edge was optimized for different materials. Stonemasons learned that shallow angles worked better for fine finishing, while steeper angles removed material faster in rough work. These refinements, small individually, accumulated into significant improvements in efficiency. Saws for stone cutting functioned differently from wood saws. Rather than teeth that cut, stone saws were smooth bronze blades that served as holders for abrasive sand. Workers poured wet sand onto the surface being cut and dragged the bronze blade back and forth. The sand particles, harder than most stone, did the actual cutting. The bronze blade simply kept sand in the cutting groove and applied pressure. Evidence of this technique appears as saw marks in ancient blocks, parallel grooves with characteristic curved striations. Drills created holes for dowels, clamps, and decorative purposes. Bow drills, operated by moving a bow back and forth to spin the drill bit, provided continuous rotation. The drill bit, often a copper or bronze tube, worked with sand abrasive just like saws. Tubular drills could bore holes several inches deep, as evidenced by drill cores, cylindrical stone pieces extracted from holes found at various ancient sites. Measuring tools brought precision to construction. Cubit rods, marked with standardized units, ensured consistent measurements across a project. The Egyptian royal cubit, about 20 inches long, was subdivided into smaller units. Surviving examples show careful division marks, some even indicating fractions. These rods allowed workers separated by distance or time to work to the same standards. Plumb bobs, simple weights on strings, defined vertical lines. Gravity pulls the weight straight down, creating a perfect reference for checking wall trueness. Ancient plumb bobs, made of bronze or stone, appear in archaeological contexts throughout the Mediterranean and Near East. Their design changed little over millennia because the basic form was already optimal. Levels determined horizontal planes. Water-filled troughs, with the water surface providing a natural horizontal reference, allowed workers to check whether surfaces were level. The chorobates, described by Roman architect Vitruvius, combined a long straight edge with a water-filled groove, creating a surveying instrument capable of establishing level lines over considerable distances. Squares ensured right angles. Bronze or wooden L-shaped tools, carefully made with 90-degree corners, allowed masons to check the squareness of blocks and corners. Larger versions helped lay out building foundations. The accuracy of these tools determined the accuracy of the final structure, making their careful manufacture essential. Ropes served numerous purposes beyond lifting and pulling. Knotted ropes with regular intervals acted as measuring tapes. Ropes stretched taut between stakes defined straight lines for alignment. The Egyptians knew that a rope formed into a triangle with sides of 3, 4, and 5 units created a right angle, a practical application of geometry. Wooden scaffolding and supports, while leaving little archaeological trace, must have been extensive. Building tall structures required platforms for workers, ramps for materials, and temporary supports during construction. The volume of timber needed for major projects likely equaled or exceeded the stone volume. This invisible infrastructure made the visible monument possible. Tool maintenance consumed significant labor. Sharpening bronze tools, repairing broken handles, replacing worn rope, all required dedicated workers. Some ancient sites show evidence of tool-making workshops adjacent to construction areas. Blacksmiths, carpenters, and rope makers supported the masons and laborists whose work was more visible. Innovation in tools happened slowly. Successful designs persisted for centuries. Yet subtle improvements accumulated. Each generation of craftsmen refined techniques slightly, passing discoveries to apprentices. This gradual evolution, not dramatic breakthroughs, characterized ancient technological development. The tools themselves were simple. Their effective use required skill, patience, and understanding developed over years of practice. In experienced hands, basic tools achieved remarkable results. Part 15. Lost Techniques and Rediscovery. Some ancient building methods vanished completely, leaving only their results as evidence. Modern researchers attempt to rediscover these lost techniques through experimental archaeology, careful analysis of surviving structures, and study of tool marks and unfinished work. This process of rediscovery reveals both what we understand and what remains mysterious. Geopolymer theory proposes that some ancient stones were not carved but cast. According to this hypothesis, builders created a concrete-like mixture from limestone rubble, water, and mineral binders, then poured it into molds. After hardening, these blocks would be indistinguishable from natural stone. Proponents point to the extremely tight joints between pyramid blocks as evidence, arguing that concrete poured in place would naturally fill gaps completely. Most geologists and archaeologists reject this theory. Analysis of pyramid stones shows natural sedimentary layers and fossil inclusions consistent with quarried limestone. Tool marks appear on block surfaces. Quarries with matching stone types exist nearby. The evidence overwhelmingly supports traditional quarrying. Yet the geopolymer hypothesis illustrates how lost techniques can spawn alternative explanations when direct evidence is lacking. Acoustic levitation represents another speculative idea. Some researchers suggest ancient builders used sound waves to reduce stone weight or even levitate blocks. This notion appears in various alternative histories and conspiracy theories. No physical evidence supports it. Modern physics confirms that acoustic levitation works only for very small objects in laboratory conditions. The energy required to levitate a multi-ton stone would be immense and would require technology far beyond ancient capabilities. More plausible lost techniques involve sophisticated rope and lever systems. Historical texts mention devices for which we lack full descriptions. Greek engineers wrote of machines capable of lifting heavy loads, but their texts survive only in fragments or later summaries. Reconstructing these devices requires educated guessing based on known principles of mechanics and the technological capabilities of the era. Experimental archaeology tests hypothetical methods. Researchers build full-scale reconstructions using only tools and materials available to ancient builders. These experiments reveal practical problems invisible in theoretical discussions. A method that seems feasible on paper may prove impossible in practice, or vice versa. Through trial and error, experimenters narrow the range of plausible techniques. One notable experiment involved moving a megalith in France. Researchers using only Neolithic tools, wooden sledges, rollers, and human power successfully moved and erected a multi-ton stone. The effort required was enormous, confirming that such projects demanded large, coordinated workforces. But it proved possible. This kind of experimental validation helps distinguish realistic scenarios from implausible speculation. Stone-moving competitions in various countries keep traditional techniques alive. Teams use historical methods to quarry, transport, and erect stones, competing for speed and efficiency. These events preserve knowledge that might otherwise disappear and generate insights into ancient practices. Participants often discover tricks and techniques not mentioned in historical sources, demonstrating that practical knowledge extends beyond written records. Toolmark analysis offers another avenue for understanding lost techniques. Microscopic examination of cuts and abrasions on ancient stones reveals information about the tools used, the direction of work, and the sequence of operations. Some marks clearly come from bronze chisels. Others suggest saws or abrasive grinding. A few remain puzzling, indicating tools or methods not yet fully understood. Unfinished monuments provide crucial evidence. When work stopped, whatever reason, the process froze in mid-action. At Aswan, partially extracted granite blocks show exactly how channels were cut and wedges inserted. At Easter Island, unfinished Moai statues lie in various stages of carving, revealing the progression from rough outline to detailed sculpture. These frozen moments teach more than finished products ever could. Computer modeling allows virtual testing of construction methods. Engineers create digital models of ancient structures and simulate different building scenarios. These simulations can reveal whether proposed techniques generate forces within acceptable ranges for available materials. If a method would break wooden beams or snap bronze cables, it can be ruled out. Conversely, methods that work in simulation merit physical testing. Some lost techniques may be simpler than we imagine. Modern researchers, accustomed to complex machinery, sometimes overlook straightforward solutions. Ancient builders, working within their technological constraints, often found elegant answers to problems we would solve differently. Rediscovering these solutions requires setting aside modern assumptions and thinking through problems with only ancient tools and materials. Other techniques may remain forever lost. Oral traditions passed from master to apprentice vanish when the chain of transmission breaks. Written records decay or are destroyed. Sometimes all that survives is the monument itself, mute testimony to vanished knowledge. We can infer general methods but may never know specific details. The process of rediscovery continues. Each archaeological excavation potentially reveals new evidence. Each experiment adds data. Slowly, the picture becomes clearer, though complete certainty about ancient methods remains elusive. What we call mysteries often simply reflect gaps in available evidence rather than supernatural or impossible achievements. Part 16. Symbolic and Practical Purpose. Ancient monuments served purposes beyond mere utility. While some structures had clear practical functions, temples for worship, palaces for governance, walls for defense, others defy simple categorization. The effort invested in their construction suggests meanings layered beyond the purely practical, meanings we can approach but perhaps never fully grasp. Pyramids combined multiple purposes. They served as tombs for pharaohs, certainly, but also as symbols of royal power and divine connection. The massive investment in construction demonstrated the state's ability to mobilize resources and labor. Each completed pyramid proclaimed Egypt's stability and strength. The precision of alignment and construction reflected Ma'at, the Egyptian concept of cosmic order and harmony. Building aligned to celestial patterns connected earthly rule to heavenly order. Religious structures often incorporated astronomical alignments. Temples oriented towards sunrise on significant dates linked ritual observances to cosmic cycles. When sunlight penetrated a doorway only on the solstice, it created a dramatic moment that reinforced religious narratives. These alignments required long-term observation and careful planning, demonstrating that priests possessed knowledge of celestial mechanics. Monumental scale itself carried meaning. A temple with columns reaching toward the sky inspired awe and suggested divine grandeur. A wall built with stones too large for any neighboring group to move asserted dominance. The aesthetic impact of size was not accidental but central to these structures' purpose. They were meant to impress, to inspire, and to endure as reminders of their builders' greatness. Some monuments may have served as community building projects. The act of construction brought people together, created shared purpose, and reinforced social bonds. Workers participating in building a temple or pyramid contributed to something greater than themselves. This collective effort strengthened group identity and cohesion. The finished structure stood as a permanent record of community achievement. Practical knowledge advanced through monumental construction. Each major project pushed the limits of current capabilities, forcing builders to innovate. Solutions developed for one pyramid informed the next. Techniques refined on temple construction applied to palaces and fortifications. Monumental building drove technological progress, creating a body of engineering knowledge that benefited society broadly. Economic impacts were substantial. Large construction projects required supply chains for food, tools, and materials. These stimulated trade, encouraged specialization, and created markets. Workers needed to be fed, housed, and paid, distributing resources through the economy. The infrastructure built to support construction, roads, harbors, administrative centers, remained useful long after projects completed. Political legitimacy derived from successful monument building. A ruler who completed a great temple or pyramid demonstrated divine favor and administrative competence. Conversely, failure to complete projects could undermine authority. This political dimension meant that construction decisions often reflected power struggles and succession concerns as much as religious or practical needs. Memory and legacy motivated many projects. Monuments were explicitly intended to preserve names and deeds for posterity. Inscriptions proclaimed who built the structure and why. The durability of stone ensured these messages would survive. In cultures without writing, architectural achievements served as permanent records, encoding history in stone. Some structures encoded knowledge. Alignments preserved astronomical observations. Proportions embodied mathematical relationships. Construction methods demonstrated engineering principles. Whether this encoding was intentional or coincidental remains debated, but the knowledge can be read from the structures themselves by careful analysis. Quarrying and construction sites themselves became sacred. Places where great labor occurred acquired spiritual significance. Quarries that yielded stone for temples became pilgrimage destinations. Construction workers might be venerated after death for their role in creating sacred spaces. The landscape transformed through construction carried layered meanings. Modern interpretations risk projecting contemporary values onto ancient motivations. We see engineering achievements and marvel at technical prowess. Ancient builders and users might have focused more on ritual efficacy or symbolic meaning. Both perspectives have validity. The structures operated on multiple levels simultaneously: practical and symbolic, technical and spiritual. Understanding ancient purpose requires humility. We view these monuments across vast temporal and cultural distances. Sources are fragmentary. Languages change or disappear. Religious beliefs evolve or are supplanted. We reconstruct context from incomplete evidence, acknowledging that our interpretations remain provisional. What seems clear is that ancient societies invested enormous resources in permanent structures because they valued permanence. In worlds where lives were brief and uncertain, stone monuments promised continuity. They connected past, present, and future, anchoring human experience to something enduring. This desire for permanence, expressed through engineering and labor, speaks across millennia. Part 17. Regional variations in technique. Ancient building traditions developed independently across the world, each adapted to local materials, climate, and cultural needs. Examining these regional variations reveals both universal principles and unique innovations. Stone construction from the Mediterranean differed markedly from techniques in the Americas or Asia, yet all solved similar fundamental problems. Mediterranean builders, particularly Greeks and Romans, favored precisely cut rectangular blocks. Greek temples showcase this approach, with column drums stacked in perfect alignment and architraves spanning between columns. The blocks fit tightly through careful dressing, creating structures of remarkable regularity. This aesthetic preference for geometric precision influenced not just construction technique but also architectural design, with buildings conceived as assemblies of standardized components. Roman concrete represented a major innovation unique to their civilization. By mixing volcanic ash, lime, and aggregate, Romans created a material that could be poured into forms and would harden into stone-like solidity. This freed them from dependence on quarried blocks for certain applications. Concrete enabled the construction of domes, vaults, and complex curved forms difficult to achieve with cut stone. The Pantheon's dome, still the world's largest unreinforced concrete dome, demonstrates the potential of this material. Mesopotamian builders worked primarily with mud brick rather than stone. The alluvial plains of the Tigris and Euphrates provided abundant clay but little suitable building stone. Ziggurats, the stepped temple platforms of Sumerian and Babylonian cities, rose from millions of sun-dried and kill-fired bricks. These structures required different engineering considerations. Brick construction demands attention to moisture protection, as water degrades mud brick rapidly. Builders used bitumen as waterproofing and designed structures with drainage in mind. Andean civilizations developed distinctive approaches suited to their mountainous environment. The Incas' polygonal masonry, with its interlocking irregular stones, appears chaotic compared to Mediterranean rectangular blocks but offers superior earthquake resistance. The technique exploited locally available stone types and responded to seismic conditions. Coastal cultures like the Moche built with adobe, large mud bricks, creating pyramids and ceremonial platforms that required constant maintenance against rare but devastating rains. Easter Island's moai, the massive stone statues, employed yet another technique. Carved directly from volcanic tuff in the Reno Raraku quarry, these statues were transported upright or horizontal, theories differ, to platforms around the island. The isolation of Easter Island meant builders worked with limited resources and no external examples. Their methods, including the distinctive topknots made from red scoria stone, developed in response to local conditions and materials. Chinese construction favored timber over stone for most buildings. Wooden post and beam structures, with sophisticated joinery and no nails, characterized Chinese architecture for millennia. Stone was reserved for fortifications, tombs, and certain ceremonial structures. The Great Wall used local materials along its length, stone in mountainous areas, rammed earth in plains. This pragmatic adaptation to available materials stretched resources efficiently across vast distances. Southeast Asian temple complexes, like Angkor Wat, combined massive stone construction with intricate carving. Sandstone blocks were shaped and fitted, then covered with elaborate relief sculptures depicting religious narratives. The scale rivals any Mediterranean temple, but the decorative approach differs, with nearly every surface receiving carved embellishment. This reflected both aesthetic preferences and the religious importance of the narratives depicted. Indian rock-cut temples represent a unique approach, subtractive rather than additive. Instead of building structures from blocks, workers carved temples directly from living rock. At Ellora, the Kailasa temple was excavated downward and inward from a cliff face, removing thousands of tons of stone to create a freestanding structure that was never assembled but only revealed. This technique required envisioning the final form before beginning and working with extreme precision, as mistakes could not be corrected. African stone construction varied widely. Great Zimbabwe's walls, built without mortar, use carefully selected granite blocks laid in courses. The technique exploited the natural exfoliation properties of local granite, which weathered into flat slabs ideal for dry stone construction. In Ethiopia, rock-hewn churches at Lalibela were carved from volcanic tuff, creating monolithic structures connected by tunnels and trenches. Arctic builders worked with materials wholly unlike stone. Inuit communities constructed with snow, ice, and bone. While not permanent monuments, igloos demonstrate sophisticated understanding of structural principles. The dome shape distributes loads efficiently, and the material, despite being frozen water, provides adequate insulation and strength for temporary shelter. This represents adaptation to extreme environmental constraints. Each regional tradition developed solutions appropriate to its context. Climate determined material durability concerns. Available stone types influenced cutting and shaping methods. Seismic activity in some regions required flexible construction, while stable areas allowed more rigid designs. Cultural values shaped aesthetic choices, which in turn influenced technical approaches. Trade and conquest spread techniques across regions. Alexander's campaigns brought Greek architectural ideas to Central Asia. Roman expansion carried concrete and arch technology throughout Europe and North Africa. The Silk Road facilitated exchange of building knowledge alongside goods. Yet despite these exchanges, regional traditions persisted, adapted rather than replaced. Understanding regional variation helps avoid overgeneralization. There was no single ancient building method, but rather a family of related approaches, each refined over generations to suit particular circumstances. Recognizing this diversity enriches our appreciation of ancient engineering achievements. Part 18. Preservation and Decay. Ancient monuments survive in varying conditions, some nearly intact, others reduced to rubble. Understanding the forces that preserve or destroy these structures illuminates both their original design and the ongoing challenges of conservation. Stone, though durable, is not eternal. It succumbs to specific processes that gradually erase even the most massive constructions. Weathering attacks stone through multiple mechanisms. Water penetrates tiny cracks and pores. When it freezes, expansion creates pressure that widens cracks. Repeated freeze-thaw cycles progressively fragment stone surfaces. This process, particularly damaging in climates with winter freezing, can reduce carved details to illegibility and structural blocks to rubble over centuries. Chemical weathering involves reactions between stone and environmental elements. Limestone, composed of calcium carbonate, dissolves slowly in acidic rainwater. Modern industrial pollution increases atmospheric acidity, accelerating this dissolution. Sandstone weathers differently, with mineral cements between sand grains dissolving or transforming, causing surfaces to crumble. Granite, more resistant, nonetheless suffers from oxidation of iron-bearing minerals, creating rust stains and surface spalling. Salt crystallization damages stone in arid and coastal environments. Groundwater carrying dissolved salts rises through stone by capillary action. When water evaporates at the surface, salts crystallize, and crystal growth generates pressure that fractures stone. This process, called salt weathering, affects many desert monuments and coastal structures. The surface develops a characteristic flaking or powdery texture as it disintegrates. Biological agents contribute to decay. Lichens and mosses grow on stone surfaces, their roots penetrating cracks and secreting acids that dissolve minerals. Plants taking root in crevices exert powerful forces as roots expand, splitting blocks apart. Trees growing atop ruins, common in abandoned sites, eventually topple walls and scatter blocks. At Angkor, massive tree roots have intertwined with temple structures, creating dramatic but destructive relationships. Human activity has destroyed more ancient monuments than natural processes. Stone from ancient buildings has been quarried for new construction throughout history. The pyramids lost their smooth limestone casing to build medieval Cairo. Roman structures were mined for marble and stone across Europe. This deliberate destruction for materials eliminated countless monuments and damaged many survivors. Earthquakes pose catastrophic risks. Many ancient sites lie in seismically active regions. Strong earthquakes topple columns, collapse walls, and crack foundations. The repeated seismic events over centuries progressively damage structures, even those designed with earthquake resistance in mind. Some sites show evidence of multiple earthquake repairs in antiquity, with builders addressing damage and reinforcing weakened sections. Subsidence and ground movement affect stability. Many ancient structures rest on alluvial soils or fill that compacts over time. Differential settlement, where one part of a foundation sinks more than another, introduces stresses that crack walls and tilt structures. The famous lean of the Tower of Pisa results from such differential settlement. Ancient builders attempted to prevent this through careful foundation design, but not all sites proved stable. War and deliberate destruction have erased monuments. Conquering armies demolished enemy structures as symbols of victory. Religious conflicts destroyed temples and sacred sites. Modern warfare, with explosives and heavy weapons, causes damage unimaginable in earlier eras. Recent conflicts in the Middle East have destroyed or severely damaged irreplaceable ancient sites. Preservation efforts attempt to slow or halt decay. Conservation scientists analyze deterioration mechanisms and develop treatments. Stone consolidants, chemicals that penetrate porous stone and harden it, can stabilize crumbling surfaces. Protective coatings shield stone from water and pollutants. Structural repairs using modern materials reinforce weakened sections without altering appearance. Documentation preserves knowledge even when physical structures cannot be saved. Photographs, measured drawings, and three-dimensional scans create permanent records. If a monument is damaged or destroyed, these records allow virtual reconstruction and study. Modern technology, including laser scanning and photogrammetry, captures details with unprecedented accuracy. Some sites benefit from their remoteness. Monuments in deserts or jungles, far from human populations, escape quarrying and development pressures. Natural decay proceeds, but slowly. These sites often survive in better condition than more accessible monuments, though vegetation and weathering exact their tolls. Climate change introduces new preservation challenges. Rising sea levels threaten coastal sites. Changed precipitation patterns affect decay rates. Increased storm intensity damages structures. Conservation strategies must adapt to these evolving conditions, anticipating future threats rather than only addressing current problems. Debate continues over appropriate preservation approaches. Some argue for minimal intervention, allowing structures to age naturally while preventing catastrophic collapse. Others favor more active restoration, rebuilding damaged sections to restore original appearance. Both philosophies have merit. The choice often depends on site-specific factors, condition, significance, available resources, and cultural values. Tourism, while providing economic justification for preservation, also threatens sites. Millions of visitors introduce wear, pollution, and vandalism risks. Managing this tension between access and preservation challenges site administrators. Solutions include visitor limits, protective barriers, and replica structures that satisfy tourist interest while protecting originals. The monuments that survive into our era have already endured centuries or millennia. Their continued survival requires ongoing attention and resources. Each generation inherits responsibility for protecting these connections to the past, ensuring they remain available for future study and appreciation. Part 19. Modern Perspectives and Continued Study. Contemporary archaeology and engineering bring new tools to the study of ancient construction. Technologies unavailable even a few decades ago now reveal details invisible to earlier researchers. Yet mysteries remain, and some may never be fully resolved. The relationship between what we know and what we can only infer continues to evolve. Ground-penetrating radar maps buried structures without excavation. Electromagnetic pulses penetrate soil and reflect off density changes, revealing walls, voids, and features below the surface. This non-invasive technique has discovered previously unknown chambers, passages, and structures at sites worldwide. At Giza, radar surveys hint at anomalies within pyramid structures that may indicate internal ramps or chambers. Laser scanning creates precise three-dimensional models of monuments. Millions of measurements captured in hours document every surface detail. These models support analysis of construction sequences, erosion patterns, and structural deformation. Researchers can measure alignments and proportions with accuracy impossible using traditional surveying methods. Digital models also serve preservation, documenting current conditions for future comparison. Geochemical analysis identifies stone sources. Each quarry produces stone with a distinctive chemical signature based on the minerals present. By analyzing trace elements in building blocks, researchers determine which quarry supplied material. This reveals ancient trade networks and logistical systems. Studies of pyramid stones confirm that most limestone came from local quarries, while granite traveled from Aswan. Experimental archaeology remains vital. Building reconstructions using ancient methods continues to test hypotheses and generate insights. Recent experiments have explored rope manufacturing, lever mechanics, and friction reduction techniques. Each experiment adds data, confirming some theories and refuting others. The physical experience of working with ancient tools often surprises researchers, revealing difficulties or efficiencies not apparent in theoretical analysis. Interdisciplinary collaboration enriches understanding. Archaeologists, engineers, geologists, astronomers, and other specialists contribute different perspectives. An engineer might recognize structural principles that an archaeologist overlooks. An astronomer can confirm or refute claimed celestial alignments. This collaborative approach produces more robust interpretations than any single discipline achieves alone. Computational modeling simulates construction scenarios. Engineers create digital models incorporating known constraints, available materials, tool capabilities, and labor estimates. Running simulations tests whether proposed methods could actually build observed structures within reasonable timeframes. Models that fail, requiring impossible forces or unrealistic labor, are rejected. Those that succeed merit further investigation. Ethnographic studies of traditional builders preserve vanishing knowledge. In regions where traditional stoneworking continues, researchers document techniques passed through generations. These living traditions often preserve methods similar to ancient practices. Observing contemporary traditional builders offers insights into how ancient counterparts might have worked. Academic debates continue over specific techniques. The Great Pyramid's construction method remains contentious, with proponents of external ramps, internal ramps, and lever-based methods each presenting arguments. These debates, while sometimes contentious, drive research forward. New evidence gradually tips consensus towards certain explanations while rendering others less plausible. Alternative theories proliferate outside academic channels. Popular books and documentaries often present fringe ideas, ancient aliens, lost advanced civilizations, or unexplained technologies. These narratives appeal to audiences but rarely withstand scholarly scrutiny. They typically ignore contradictory evidence and misrepresent archaeological findings. Academic researchers spend considerable effort countering misinformation. Public interest in ancient mysteries supports research funding and preservation efforts. When people care about ancient monuments, resources flow toward their study and protection. Educational outreach, explaining what we know and how we know it, helps audiences appreciate both ancient achievements and modern scientific methods. Unanswered questions remain numerous. We cannot know with certainty how specific blocks were moved or lifted. We cannot fully understand the organizational systems that coordinated labor. We cannot read the minds of ancient engineers or appreciate their subjective experiences. These limits are inherent in studying distant past from fragmentary evidence. Yet the accumulation of knowledge over decades of research has illuminated much. We understand general principles even where specific details elude us. We recognize the sophistication of ancient engineering and the capabilities of ancient societies. We appreciate that monuments resulted from human intelligence, organization, and labor, not from supernatural intervention or lost high technology. Future discoveries will revise current understanding. Archaeology regularly uncovers unexpected evidence. New analytical techniques reveal information in artifacts studied for decades. The story of ancient engineering remains unfinished, continuously refined as knowledge accumulates. Each generation of researchers builds on predecessors' work, adding layers of understanding. The monuments themselves endure as primary evidence. Stone blocks bear tool marks, quarries preserve extraction methods, and structural features reveal design principles. These physical records remain available for study, potentially answering questions we have not yet learned to ask. The stones wait patiently, holding their secrets, gradually yielding insights to those who examine them carefully. As we approach the end of our exploration, the ancient world's engineering achievements stand before us, less mysterious perhaps than when we began, but no less impressive for being understood as human accomplishments. Part 20. The Human Achievement. We have journeyed through quarries and across construction sites, examined tools and techniques, traced the movement of massive stones from bedrock to monument. Throughout this exploration, one truth emerges clearly. The engineering marvels of the ancient world were not mysteries in the supernatural sense, but achievements of human intelligence, persistence, and collaboration. The builders who raised pyramids and temples possessed no lost advanced technology. They had stone, bronze, wood, and rope. They had geometry, observation, and accumulated experience. Most importantly, they had time and organized effort. A project spanning decades allowed for patient, methodical work. Mistakes could be studied and corrected in subsequent phases. Knowledge passed from master craftsmen to apprentices, each generation refining techniques inherited from predecessors. Modern viewers, accustomed to rapid construction enabled by steel, concrete, and powered machinery, sometimes struggle to comprehend achievements made with simpler means. This incomprehension breeds speculation about aliens, lost civilizations, or unknown technologies. Such speculation, while imaginative, misses the more profound truth. Ancient builders were fully human, possessing intelligence equal to our own. They solved problems using available resources and developed sophisticated engineering knowledge through observation and experimentation. The precision we observe in ancient structures reflects not mystery but skill. A mason who spent years dressing stone developed an intimate understanding of material properties, tool behavior, and efficient techniques. Communities of such skilled workers, supported by organized labor systems and administrative structures, could achieve remarkable results. The monuments testify to what humans can accomplish through focused, sustained effort. Cultural motivations drove these achievements. Societies invested enormous resources in construction because monuments served vital purposes. They proclaimed power, honored gods, preserved memory, and unified communities. The practical engineering challenges were means to these larger ends. Understanding ancient construction requires recognizing both technical and cultural dimensions. Regional variations remind us that many solutions exist to similar problems. Mediterranean, Andean, Asian, and African builders developed distinct approaches suited to local materials and conditions. No single correct method exists. Ancient engineering was pragmatic and adaptive, evolving in response to available resources and accumulated experience. Some details remain uncertain and may always elude complete understanding. We reconstruct methods from incomplete evidence, acknowledging gaps in knowledge. This uncertainty does not diminish ancient achievements. Rather, it reminds us of the distance separating us from these cultures and the fragmentary nature of historical evidence. Modern study continues revealing new information. Archaeological excavations uncover worker villages, tool workshops, and quarry sites. Advanced imaging technologies peer inside structures without invasive procedures. Experimental archaeology tests hypothetical methods, confirming or refuting proposed techniques. Each discovery adds detail to our understanding, though complete certainty about every aspect remains impossible. The monuments themselves endure. Some survive nearly intact, still proclaiming the capabilities of their builders. Others lie in ruins, victims of time, nature, and human activity. Even ruined, they teach us. Tool marks on scattered blocks, alignments visible in remaining courses, structural features in partially collapsed sections, all contribute evidence. Preservation efforts attempt to protect what survives. Conservation science develops methods to slow decay and stabilize damaged structures. Documentation creates permanent records against future loss. These efforts reflect our recognition that ancient monuments belong not just to the nations where they stand but to all humanity as evidence of our shared past. The human story told by ancient engineering is one of problem-solving, creativity, and determination. Faced with challenges, transporting massive stones, achieving precision with simple tools, coordinating large workforces, ancient societies developed solutions that worked. They learned through trial and error, building on successes and learning from failures. This process of gradual refinement over generations produced the techniques that raised monuments. We honor ancient builders not by attributing their achievements to supernatural forces or imaginary advanced technologies, but by recognizing them as skilled, intelligent people who mastered their crafts. They were engineers in the truest sense, applying systematic knowledge to practical problems. They were organizers who coordinated complex projects. They were artists who shaped stone into forms of enduring beauty. As you drift towards sleep, let the image of ancient workers settle in your mind. See them in quarries, striking stone with patient rhythm. Watch them pull ropes, moving blocks across desert sand. Observe them checking surfaces with simple tools, grinding away imperfections grain by grain. These were people like us, facing problems and finding answers, building not for themselves alone but for ages they would never see. Their monuments remain, weathered but standing, bearing witness to human capability. We walk among stones shaped by hands long turned to dust, yet those hands' work endures. This is the true marvel, not that ancient engineering seems impossible, but that humans made it possible through knowledge, skill, and collective effort sustained across generations. The mysteries of ancient engineering, when examined closely, resolve into human stories of work and ingenuity. The stones were moved by people who understood leverage and friction. The joints were fitted by masons who knew their craft. The alignments were achieved by observers who watched the sky patiently. No magic was required, only the application of intelligence to persistent problems. Sleep now, surrounded by the quiet presence of ancient knowledge. The stones stand in darkness as they have for millennia, holding their builders' understanding in every fitted joint and carved surface. That understanding came not from gods or aliens, but from human minds confronting challenges and discovering solutions. This makes the achievements no less impressive. If anything, recognizing ancient engineering as purely human accomplishment deepens our appreciation and connects us across time to those who built wonders that endure.